All right, here we go. For today, we're going to be talking about energy, light, and atomic spectra. This information is important because in order to understand the nature of the electron configuration, we've got to understand where that information came from. We're going to start with a little bit of background information on really the wave nature of light, what light is, and what we know about light. Light is a form of electromagnetic radiation. Other types of electromagnetic radiation are things like radio waves. You can talk about cell phone waves, microwaves, infrared. All of these are different types of electromagnetic radiation. They're really the same type of energy. Really the difference is how long the waves are. Visible light is just a small part of the overall electromagnetic spectrum. Visible light is from about 750 nanometers to around 400 nanometers. And all the colors in between are really the colors of the rainbow. When we look at waves and wave properties, we can really talk about a few features of waves. The first has to be wavelength. So wavelength is really just the distance from one crest to the other. We use the Greek letter lambda in order to represent wavelength. The Greek letter lambda, in my mind, looks a little bit like a backwards H that's hunched over to the left. Anyway, wavelength is important because wavelength ultimately determines the color of the light. If you look at this diagram, the longer the wavelength, those are in the red part of the spectrum, whereas shorter wavelengths, those are in the blue or purple part of the spectrum. The other thing just to make note of is the amplitude of the wave, that is the height of the wave. That's ultimately what determines how bright or dim light is. The other thing that we talk about is frequency. For frequency, we use the Greek letter nu, which to me it kind of looks like a V that's blowing in the wind. It's sort of bent over a little bit. Frequency is just the number of cycles that pass through a stationary point at a given time. Frequency is measured in the units hertz, which is an inverse second. So it's cycles per second. And then the other thing that is worth mentioning is that all electromagnetic radiation travels at the same speed, which is the speed of light. This speed is 3.00 times 10 to the 8th meters per second, and that's true for light in a vacuum. So light traveling through outer space, for example, travels at that speed. There is some relationships that are worth noting between wavelength and frequency. It's given by this equation. C is equal to wavelength times frequency. And that ultimately tells us that there is an inverse relationship between wavelength and frequency. That is, if wavelength increases, the frequency decreases. And if wavelength decreases, then frequency increases. So shorter waves pass a given point more rapidly than longer waves. And also, just so we're familiar later on, we can algebraically rearrange that equation so that we set the speed of light divided by the wavelength that will tell us the frequency. It also is important to note that we measure wavelength in units of nanometers, and so we need to know this conversion that 1 meter is 10 to the 9th nanometers. So the next thing to talk about before we get into how we use light to learn about atomic structure is we're going to talk about the particle nature of light. So this was actually a pretty remarkable discovery. And ultimately, it's this photoelectric effect that led to the conclusion that light is photons. So basically what happens is they did some experiments. Here we have the basic setup of the apparatus where you take some metal surface in a vacuum and shine light on that metal surface. And the observation is that that light can eject electrons from the metal surface. That is, if the light has enough energy. And so that photoelectron effect leads to several kind of questions and observations that follow. Kind of the classic understanding of light predicted that the intensity or the brightness would affect the rate that the electrons are ejected. In other words, if you shine a brighter light, then the expectation was that more electrons would be ejected. However, scientists observed that it was the frequency, not the brightness, but the frequency that was the factor that really determined if an electron is ejected. In other words, a high frequency light that is dim does eject an electron. So even if the light is low intensity, we still get a photoelectron effect. It has to do with the frequency. So this actually is a pretty remarkable discovery because it means that light isn't a continuous stream of a wave. Rather, light comes in little packets of energy. So this was actually first proposed by Einstein, that light energy comes in packets, and Einstein called those photons. And he used this equation to actually calculate the energy of a photon. So E equals h nu, and that equation E is energy. H is what is known as Planck's constant, and you'll notice it's a very, very small number, 6.626 times 10 to the minus 34th joules per second. And that's multiplied by frequency. And this is important because this gives us a relationship ultimately between the wavelength of a light and the amount of energy that it has. So if you recall back, we rearranged our original equation for light so that we were solving for wavelength. Well, if we do a little mathematical substitution and we plug in c over lambda in the place of frequency, the new equation is energy is equal to Planck's constant times the speed of light divided by wavelength. In other words, we have a relationship between energy and wavelength of light. In summary on this page, the photoelectric effect is evidence that light comes in packets, and those packets we refer to as photons. And also from the equation, there's a relationship between energy of light and the wavelength. And that relationship is actually an inverse relationship. So long wavelengths end up with low energy light, and short wavelengths are high energy light. So if we go back to our electromagnetic spectrum, so the ones that are shorter wavelength, if we're in this purple part of the spectrum, that's high energy light. The ones that are longer wavelength, if we're in the red part of the spectrum, that's low energy light. And also outside of the visible part of the spectrum, ultraviolet light is even higher energy. X-rays and gamma rays would be higher energy than that. And this is also why, like if you think about ultraviolet light can be damaging to skin, that's because those photons, that electromagnetic radiation, is going to be higher energy. Whereas, we don't worry so much about things in this part of the spectrum like cell phone or radio waves. Those pass through our bodies and we encounter those all the time, but they're very low energy types of electromagnetic radiation, so they're not really a problem for us. And so here's where we start to make connections between the energy in light and atomic spectrum. So it was actually Niels Bohr who started to analyze atomic spectrum. And essentially what he did, atomic spectra is the study of electromagnetic radiation absorbed and emitted by atoms. Essentially what Niels Bohr did was he took hydrogen gas that was trapped inside of a glass tube, and he passed electric current through that hydrogen gas and found that the gas would glow, produce light. And he would take that light and pass it through a prism, and that prism separates the wavelengths. And what he did was then he produced a what's known as a atomic spectrum. So in this diagram, this is showing us the atomic spectrum for hydrogen. So ultimately, we need to be able to explain why we get just specific colors of light rather than colors of light that might be in between these bright lines. So it's important to know that when an atom absorbs energy, and there's different forms of energy, it could be heat, light, electricity, those atoms will re-emit that energy as light. It was observed that light emitted from elements such as hydrogen, helium, barium only contain certain wavelengths. So a continuous spectrum, like the white light on the bottom, would have all of the colors of the rainbow. But certain elements, helium, barium, when they produced a spectrum, there's only specific lines of color. So there's black spaces in between where no photons, no light is produced in that wavelength. And so we need to come up with an explanation why. Niels Bohr is the one that developed an atomic model to explain these atomic spectra. The energy, he basically just said that the energy in each orbit must be quantized. When electrons transition from one quantized orbit to another, distinct amounts of energy are emitted. And so basically he said that an energy or an electron can be promoted to a higher energy level, and that is by absorbing energy. And as it returns back down to a lower energy level, light is emitted. And he made the connection that basically those specific lines of color that were observed in the atomic spectrum correspond to distinct changes in energy. So a small change in energy from energy level, say 3 to 2, would produce a lower wavelength photon, in this case red. And then a bigger change in energy from, say, 4 to 2 would produce a higher energy photon. An even bigger change in energy, say from energy level 5 all the way down to 2, would produce an even higher wavelength. And so basically Niels Bohr explained that electrons can only exist at specific energies. They cannot exist between, because if an electron went from energy level 2.5 down to 1, then we would expect to see a photon somewhere corresponding to that energy range. But we only get specific photons because there's only specific energy transitions possible. And ultimately, Bohr was able to calculate the energy of an electron. So he used this equation, energy is equal to this number, negative 2.178 times 10 to the minus 18th joules, which that number is known as Rydberg's constant. Multiply that by nuclear charge divided by the principal energy level squared. For hydrogen, since it only has one proton, its nuclear charge is 1. And so Bohr actually did these calculations, and he found that at energy level 1, you can calculate a specific quantity of energy. At energy level 2, you can calculate a specific quantity of energy. And so Bohr ultimately worked out where all of these energy levels lie and was able to connect those energy levels to specific wavelengths of light as electrons make those transitions. So going from energy level 3 to 2 produces a red photon. And by the way, you may wonder why we're always dropping to 2. It turns out that there's kind of a big gap between 1 and 2. So any transition down to the first energy level, those produce very high energy photons in the ultraviolet part of the spectrum. And some of these transitions between, say, like 3 and 4 would produce very low energy in that infrared part of the spectrum. So with this, we can actually calculate the energy of, or the change in energy as a result of these photons moving from one level to another. So this relationship can be used to calculate the wavelength of a photon emitted as a result of a specific change. If we go back to the previous equation, if we calculate the energy level, or the energy for energy level 2 and plug it in, and we calculate the energy at energy level 3 and plug it in, we can predict the energy of that photon. And we can actually then turn it around and predict the wavelength of that photon by plugging it into our rearranged equation. So, with all this information, we've learned quite a lot about atomic structure, and basically that electrons exist in specific energy orbits, and those energy transitions can be calculated and found. I'll just leave you with this then, that when you look at fireworks and you see all these bright colors, really what you're watching is electrons transfer from higher energy levels to lower energy levels. When those fireworks explode, those exothermic reactions release a lot of energy. That energy, it is sometimes enough to excite electrons to higher orbits, and then those electrons in the atoms fall back down to lower orbits, and as they do, they emit colors. Different elements produce different colors of light, and so we get a fair amount of enjoyment from watching those electrons drop from excited states to ground states. So I will leave you with that. It is important that you get these notes down into your notebooks, and we are going to have some more opportunity to look at these concepts and ask questions. And by the way, this is chapter 7, so as you're taking these notes down, you should be doing some reading along with it. So we will see you all on Tuesday. Thank you.